Hi everyone, welcome to Bean's channel. Today we will continue our learning of the deep learning book. And in this lecture, we will go with chapter 3, probability theory and information theory. And it's another very fundamental mathematical tool that is very useful and powerful for our further study of machine learning and deep learning. Probability theory is a mathematical framework to represent uncertainty. It's a fundamental tool of many disciplines of science and engineering. In my opinion, it's a more interesting part than linear algebra because you can use it to explain many things in life, such as card games or insurance options. But this chapter is not a very comprehensive survey of all of probabilities. It only quickly reveals the core concepts and ideas that are most relevant to the field of deep learning. And it will teach you enough to read this book. But I highly recommend you to consult another probability course, and I have listed two great resources here. First, let's start with the most basic concept, random variables. A random variable is a variable that can take on different values randomly. And this can be a discrete variable or continuous variable. And usually we denote random variables with a lowercase letter in plain interface like this. And we denote the values it can take on with lowercase script vectors like this. For these random variables, it has two states, x1 and x2. A very simple example of the random variables is the result of coin flipping. It's a discrete random variable and has two possible states, head or tail. A random variable is just a description of the states that are possible. So it must be coupled with a probability distribution that specifies how likely each state is. And the way we describe probability depends on whether the variables are discrete or continuous. For discrete random variables, we use probability mass function to describe its probability distribution. And this function must satisfy the following three properties to become a reasonable PMF function. The first one is that the domain of P must be the set of all possible states of X. And the second property is that the values of the function P should be between 0 and 1. In probability theory, an impossible event has probability 0, and no state can be less probable than that. Likewise, an event that is guaranteed to happen has probability 1, and no state can have a greater chance of occurring. The third property is called the normalization property. That is, the summation of all values of the probability should be as exactly 1. So without this property, we could obtain probabilities greater than 1, which is have no sense. An example is the uniform distribution. In this distribution, it makes each of its states equally likely. Suppose we have say k different states, and so the probability of each state should be 1 out of k. When working with continuous random variables, we describe probability distributions using a probability density function. It also needs to satisfy the following three properties, which are very similar to the discrete situations. But we just adapt it to the continuous situation. The main difference lies in the second property. In these properties, we only request the values be non-negative. and we do not require the value be strictly less than or equal to 1. And in the third property, we replace the summation by the integration. An example is the uniform distributions over continuous variables. It's if the distributions is performed on an interval between A and B, where A and B are the endpoints of the interval with B is larger than A, then the PDF function should be exactly like this. Sometimes we know the probability distribution over a set of variables, and we wish to know the probability over the subset. And this probability distribution is called the marginal probability distribution. We can get the marginal probability distribution using the sum rule. Here, suppose we know the joint probability of P xy, and we hope to get the marginal probability of Px. Then we can do the summation over all possible values of y, and we can get what we want. The first one is the continuous discrete situations, and in the continuous situations, we can do a very similar operation by replacing the summation operation with the integration. In many cases, we are interested in the probability of some event, given that some other event has happened. This is called a conditional probability. It's represented like this. It means the probability of y equal to y, given that x being equal to x. And it can be computed with this formula. So any joint probability distribution over many random variables may be decomposed into conditional distribution over only one variable. This is known as the chain rule or product rule of probability. It follows immediately from the definition of conditional probability. Two random variables x and y are independent if their probability distribution can be expressed as a product of two factors, one involving only x and the other one involving only y. So in this case, suppose we have two random variables x and y. If their joint probability can be factorized like this, we can get the conclusion that x and y are independent. Another concept is the conditional independent. Two random variables are conditional independent, giving another random variables if the conditional probability over x and y can factorize in the similar way. Okay, next we will get familiar with some metrics of the probability distribution. The first one is the expectations or expected values. The expectations of some function f over a random variable x is computed like this. The first formula is for the discrete random variables, and the second one is for the continuous case. You can see that this value is considered as the average or mean value that f takes on when x is drawn from the probability distribution P. You can understand this metric like this. if you have only one trial to get the values of the functions, the safest assumption is the expectations. It's also the average of the mean values. The expectations has this linear property. Variance. Variance is used to measure how much the function values vary as we sample different values of x from its probability distributions. It is computed by this formula. And covariance. Covariance gives some sense of how much two values are linearly related to each other, as well as the scale of these variables. And it's very useful to get to know the difference between two random variables. But we should know that the notions of covariance and dependence are related, but are in fact distinct concepts. If two variables are independent, they have zero covariance. By contrast, if two variables have zero covariance, there must be no linear dependence between them, but they may have some non-linear relationships. In other words, it's possible for two variables to be dependent, but have zero covariance. So if we now have a random vector, we can compute this covariance matrix. And the diagonal element of this matrix just gives the variance. Next part, we will learn some common probability distributions. They are simple but very useful in many contexts in machine learning and deep learning. The first one is the Bernoulli distribution. It's a distribution over a single binary random variables. And this, which means that the variable can only have two states, 0 or 1. This distribution is controlled by a single parameter, which gives the probability of the random variables being equal to 1. And these are some properties of this distribution. A multi-Bernoulli distribution is an extension of Bernoulli distributions. In these distributions, the random variables can have k different states, and in this case, it's parameterized by a vector. In this vector, every element indicates the probability of each state. Gaussian distributions. It's considered as the most famous and most commonly used distributions over real numbers. And it's also known as the normal distributions. And Gaussian distributions are a sensible choice for many applications and are usually good default options in the absence of prior knowledge. And the formula of Gaussian distributions is in this way, and it has two parameters. The first one is the mu, which is a real number. It represents the mean of the distribution. And the second parameter is the sigma. It should be a positive real number, and it denotes the standard deviation of the Gaussian distributions. And sometimes we present the Gaussian distributions in this way, and parameterized by precision beta, which is the inverse variance of the distribution. This figure is a plot for the density function. It exhibits a classic bell curve shape with the x-coordinate of its central peak given by mu, and the width of its peak controlled by sigma. In this In this example, we depict the standard normal distribution with the mu is being equal to 0 and sigma being equal to 1. We can generalize the Gaussian distributions to the vector field. And here we call this multivariate Gaussian distributions. In these distributions, the formula is very similar, but we use the covariance matrix instead of the deviation real number. And the mu also become a vector. And we can also get the precision matrix based formula. In the context of deep learning, we often want to have a probability distribution with a sharp point at 0 point. To accomplish this, we can use the exponential distributions. The curve of this distribution is like this, and the right is its formula. And you see the domain of this function is all non-negative real values. Leftler's distribution is a close related probability distribution that allows us to place a sharp peak at an arbitrary point mu. It has this symmetric property. In some cases, we wish to specify that all of the mesh in a probability distribution clusters around a single point. This can be achieved by defining a PDF using the direct delta function. This function is called direct delta function. In this function, it's 0 valued everywhere except mu, but it integrates to 1. It's not an ordinary function, but a so-called generalized function. And because it's defined in terms of its property when integrated. And the curve of this function is like this. A common use of the direct delta distribution is as a component of an empirical distribution. Its formula is like this. You see it puts probability mass 1 out of m on each of its points. With some simple probability distributions, we can get more complex probability distribution by combining the simpler ones. One common way is to construct a mixture distribution. And the idea is this. On each trial, the choice of which component distribution generates the sample is determined by sampling a component identity from a multi-node distribution. So you say that that's some distribution Px, and we can have a multi-node distributions to do the mixture things. This figure is an example of the Gaussian mixture model with 3 components. And next part, we will get to know some very useful functions that is very useful in the machine learning field. The first one is the logistic sigmoid. And the left is the figure of this function, and the right is the formula. You see in these functions, the output values is strictly between the 0 and 1. And therefore, this function is commonly used to parameterize Bernoulli distribution. Another commonly encountered function is the soft flat function. Its name comes from the fact that it's a smooth or softened version of the max function. Then the left figure is its curve, and the right is its formula. From the curve, we see that this is really it's very similar to the max functions, but it's obviously a soft version. These are some nice and useful properties of these two functions. They are very useful to simplify some algorithms, and I think you may find these properties extremely useful when we go further in this deep learning book. In many situations, we know the probability of y given x, and we wish to know the probability of px given y. To get this, we can use the Bayes rule, and the formula is like this. It's very straightforward to derive from the definition of conditional probability. Know that while py appears in the formula, it's usually feasible to compute it using the second equation. So we don't need to begin with the knowledge of py. If we know the probability distribution of pyx, we can derive the probability distribution of pxy. Information theory. Information theory is really very beautiful, elegant, and powerful. It's a branch of applied mathematics that revolves around quantifying how much information is present in a signal. It was originally invented in the communication engineering, such as sending messages via radar transmission. In that context, information theory tells how to design optimal encoding schemes. This theory currently become fundamental to many areas of electrical engineering and computer science. The very basic intuition behind this theory is that learning that an unlikely event has occurred is more informative than learning that a likely event has occurred. Let me give an example. A message saying the sun rose this morning is so uninformative, but a message saying there was a solar eclipse this morning is very informative. So based on this intuition, we can have the definition of self-information. Its definition is by this formula. It's very simple. It's just the negative log of the probability. You'll see in these definitions, if the probability is high, and then the self-information is low, and if the probability is very low, then the self-information is high. But it's not that the self-information deals only with one single output. We can quantify the amount of uncertainty in entire probability distribution using the Shannon entropy. And the formula of the Shannon entropy is this. It can be considered as the expected amount of information in an event drawn from that distribution. You see, this definition is actually the expectations of the self-information. The Shannon entropy gives a lower bound on the number of bits needed on average to encode symbols drawn from the distribution P. This is a plot of the Shannon entropy of Bernoulli variables. And it just shows that the distributions that are closer to deterministic have low entropy, where distributions that are close to uniform has a high entropy. And let's look at this. You see in the endpoint, if the probability is close to 0 or close to 1, it means that this event is more deterministic. Then the entropy is very low and very close to zero, and we get the highest entropy when this event is when the probability of this event is a half, which is at the most uncertain level. This is a really interesting definition. KL divergence is performed over two probability distributions. It can be used as a matrix to measure how different these two distributions are. And it's noted that this KL divergence is asymmetric, as shown in this figure. Suppose we have a distribution P, which is a mixture of two Gaussians, and it's shown in this figure. We have this distribution P, and the problem is that we want to approximate it with an unknown single Gaussian Q. And so that these two figures shows the effects of the directions we choose. So for different, if we choose different directions, we may get two very different solutions. And so we should get this in our mind, and the choice of which direction of the KL divergence is problem dependent. We should know that. Another concept is the cross entropy. Cross entropy is very related to the KL divergence. And you can see this is its definition. The cross entropy between P and Q is a standard entropy of P plus the KL divergence between P and Q. And the second formula is another formula that is equivalent to the first one. We should note that minimizing the cross entropy with respect to Q is equivalent to minimizing the KL divergence, because the Q does not involve in the first factor of this formula, so it is equivalent to minimizing the KL divergence. Cross entropy is also a very widely used loss functions in our machine learning, which we will know in our further study. Structured probability models, also called graphic probability models, is another very elegant and powerful subfield of the probability theory. It's a very big subfield, but today we only need to know some very basic insight of it. We should know that a probability model is a model that uses a graph express the conditional dependence between random variables. So usually in some real problems, we will have many random variables in a problem, and then we can use the structured probability models to describe its relationship and dependency between the different random variables, and we can use it to model the real problem. There are two main kinds of structured probability models: directed and undirected. The directed models use graphs with directed edges, which is shown in the left. And this edge can be understood as the dependency relationship between the random variables. And this directed model is very straightforward to understand. And in these models, we can just decompose the joint probabilities into some factors of conditional probability. On the left is the undirected models. It can also be used to describe the relationship between different random variables. But because we use undirected edges, we don't know the dependency between the random variables. We just know these two variables are interacted or has some relationship, but we don't know if it has some dependency. And in the situations that we don't know the exact dependency of or there is no dependency between the random variables, we can use this undirected model. In this case, we just know the two variables are related. But in these models, we can get the joint probabilities by these functions. We should know that these functions are not probability distributions. They are just some functions. They just need to be non-negative. So a normalization constant z is needed to let it satisfy the normalization probability of the probability distribution. So actually, these two models are very complicated, and maybe we will get to know more about these models when we go very further in our study. Wow, we have done with chapter 3. And in this chapter, we review the very basic concepts of probability that are most relevant to deep learning, but in a very quick and rough way. If you have no exposure to probability, I think it's enough to let you continue the study of deep learning, but I highly recommend to refer to some resources focused exclusively on probability theory. In next lecture, we will go with one more set of fundamental mathematical tools, that is numerical methods. Thank you very much, and I appreciate your watching. If you find my video useful, please make a subscription. I appreciate it. Currently, I'm considering making another episode that can introduce some state-of-the-art research and development in the field of AI. Because this field is a very active field, and every week, every month, we have some very new and great improvements. So I hope to introduce some of these improvements, and in this episode, there will be less math, and I think it can be more interesting and more beginner friendly. So see you next time. Bye bye.